Hello, and welcome to Aerospace Testing International's podcast, Testing Talk. I'm pleased to be able to bring you this interview with two experts from material supplier Greene Tweed, Mease and Sebastien Kohler. The company initially caught my eye with some case studies it had published about new composites that they claimed could replace components and structures in aircraft that previously had to be metal. I was curious about the materials and the testing that gives the company confidence to make this claim. And as you will hear in this interview, it's the catalyst for quite a deep dive into material science and composites in aircraft. Hello guys, thanks for joining me this morning. We're going to talk about composites versus metallic components and where that's going. But I would first like you just to introduce yourselves and the company, if you could please.
Thanks, Ben. Excited to be here. My name is Mease. I'm the product manager for our Thermoplastic Composites product line, located in Philadelphia, and I've been with the company for about 18 years now.
Good afternoon, Ben. I'm Sebastien Kohler. I'm a senior scientist for Greene Tweed's Structural and Engineered Components business unit, which is basically composites. And I'm located in Switzerland. I've been with the company 7 years.
Travis, could you give me some of the background on the company? I mean, how do you work with the aerospace sector? Where do you fit in within the supply chain?
Yeah, sure. So Greene Tweed is a privately held organization. We've been around for about 160 years, global presence, about 1,900 employees. And we first got started in the aerospace industry in the 60s, making elastomers for F4 landing gear. And that gradually progressed to including scrapers and hard plastics in the 80s and 90s. And then we eventually started adding more fiber, longer fiber, higher ratios, and transitioned into composites manufacturing after that. So we are a component provider, a solutions provider, focusing on non-metallic solutions, elastomers, composites, injection molding, typically compression molding. We have all the ancillary capabilities to support any sort of design optimization, product testing, validation, etc.
Great. Thanks, Travis. Could you talk to me about replacing metallic components with thermoplastic composite ones? Why would we do that? What are the benefits? Could you talk around that, please?
Yeah, sure. A lot of our focus has been on discontinuous long fibers or chop fibers or forged fibers, as they're sometimes called. So we have a pretty unique process where we can have a very high carbon fiber content, 60% by volume, 70% by weight. And what we're doing is we're bringing in a unidirectional pre-preg roll, chopping it up, changing the form, etc. And that allows us to compression mold highly complex shapes. So really the value proposition is in replacing metallic components, something that might start off as a billet of material, a block of material that has a lot of CNC machining, a lot of material waste associated with that. So we're chasing certainly after weight savings, right? That's the primary goal. There's a lot of value within aerospace and defense to remove weight. So if we do a black metal part, a density 1-to-1 swap, we're about 42% lighter than aluminum solution. Typical application weight savings around 35 to 50%, depending on loads, mechanical factors, environmental factors. If we can consolidate parts, sometimes that increases the weight savings. If there's multiple brackets that are bolted together, you reduce fasteners, reduce part node count. The other thing too, we've seen one of the benefits of utilizing, composites versus traditional aluminum products. We've gone to OEMs, tier ones, and you see these beautiful composite nacelles, highly engineered, but then there'll be metallic brackets and widgets bolted up to it. So they require painting, they require isolation, they require priming as well due to galvanic factors. It also introduces CTE mismatch, coefficient of thermal expansion mismatch. So a lot of benefits for transitioning to composite solutions. And I think it's something that we've seen in the marketplace that really hasn't been identified, the higher strength, more complex shape composite solutions.
So those weight savings translate directly into fuel savings for airlines operating the aircraft. But where in the supply chain is the cost really coming from? Is it the manufacturing process or is it the cost of the materials?
So it's essentially the cost to procure the product. So there's a lot of the things that are associated with that. That's the material, that's processing, that's inspection, that's all the things that go into it. But the end result is the savings for the airline, for the operator. I think we've had different figures floated to us depending on where it is on the aircraft. If an engine, we have figures floated to us, I think anywhere from $400 to $800 per pound saved, and basically a backwards calculation for the fuel consumption. Different markets have different values associated with that weight savings. I think AAM, eVTOL places a higher value on that. Certainly like satellites in space places a higher value on that. There's more fuel burn per unit mass.
Okay, great. I mean, I know about a lot of interior components used in cabins, but using them for structural components is obviously more challenging and more critical. Sebastien, can I bring you in here? I mean, where does it make most sense to use these types of components on a plane?
Well, I think the first thing to understand is something that Travis highlighted is we're not just replacing any metal with composite. Our value proposition is in the complex shape parts. Due to the technology we're using, no pan. So you will never see a wing or a fuselage made by Greene Tweed. That is not where we are active. And so in the complex shape part space, it is where you have a lot of machining, a really complex shape. The coin term, I think, in the aerospace industry is the buy-to-fly ratio. The higher your buy-to-fly ratio, the better we play, because although we use a material that is quite expensive, we net mold it or near net mold it. And so we have next to no waste of our material.
Okay, so when you say complex geometries, complex shapes, how complicated can you get? And what sort of parts are we talking about replacing?
We have different product families. One is the one you probably think most readily of is structural brackets. So brackets, ribs, fittings, and everywhere around it. How complicated depends on, well, the application, obviously. It needs to be moldable. And admittedly, we've become quite good at molding and making molds, so we can go to a fairly high degree of complexity. You should not expect us to have as high a shape complexity capability as injection molding due to the material itself, right? But we can still do fairly complex shapes. We've written a few articles about it. We will be at the Fun Bro show for those of you who want to visit, with many, many different prototypes and parts demonstrated to showcase. So that's really the first big family. We are also working on airflow structures, where the key factor is that one surface has to be very controlled, smooth, because there's airflow on it. And typically, what we started with were parts where the back face would need structural reinforcement. That's where the shape complexity capability of DLF allows us to build in reinforcement structures, gussets, ribs, attachment points, with potentially molded in inserts or holes and everything that you would not do on a traditional composite. That's the second family. That then led to the more recently and also published vanes product line, where obviously if it's a vane, both sides are aerodynamic structures or surfaces that need a tight profile, tolerance and smoothness. The value proposition there being that we can mold in all the attachment and all the end fittings and everything at the same time as we do the profile.
Okay, thanks for the overview there, Sebastien. I appreciate it. Can I just clarify something, Travis? I mean, when I talk about composites, I normally think about laying up and big components, but here you're talking about molding. It's a thermoplastic composite. Is that a unique thing to Greene Tweed, or is it a fairly common approach?
What we're doing is a bit unique. Typically speaking, you have thermoforming, thermostamping, multiple ways to process thermoplastics, but that's traditionally supporting continuous fiber solutions. So we were looking to provide more complex shapes, and the way that we're doing that is via compression molding. We have to do it via like a short fiber too. So what compression molding is, essentially we have a steel tool, steel mold. It's multiple pieces depending on complexity, can be somewhat like a jigsaw, but we'll put the material into this mold. The operator will then close it up, and then we process it via multi-stage press, which applies pressure, applies temperature. There's no chemical reaction for a thermoplastic, unlike a thermoset. So essentially that press processes it, the material cools down, it solidifies, you pull it out, the operator disassembles the tool and pulls out the part, and then you can repeat the process, clean the tool, apply mold release, put material back in. And that's essentially what we're doing. That's the process in a nutshell.
Okay, thanks. So I'd like to get down into the detail a little bit more here and talk about the testing regime, specifically when we're talking about taking a metallic component out for a thermoplastic composite one. How does that change what you're doing regarding testing? How do you make that decision that it's something that can happen? Could you talk me through that?
Yeah, sure, Seb. I'll take the first part, and I'll pass it on to you for some details. But essentially what we're doing is we're collaborating with OEMs, tier ones, and they'll bring to us a metal part or some sort of design request, a statement of work, some sort of flow down of requirements. And we have the ability to optimize that component itself and to analyze it. So we have the ability to predict how that fiber is going to flow throughout the tool. We have the ability to run an FE analysis, nonlinear support. And then essentially what we're going to do is, from a certification perspective, we're never going to cert by analysis. It's always going to be a point design approach. What that means is you're always going to have to go out and break a couple parts and validate what you're doing. What you predicted is actually occurring on the parts. So I think we've created a lot of different methodologies to reduce risk. We want to get it right the first time. That reduces risk to cost, reduces risk to schedule. And essentially what we're doing is we're trying to optimize that part as much as we can, size it appropriately, get the weight margin out. But then when it comes to that predictive capability, I'm going to pass it over to Sebastien. I think you have a little bit more insight on it.
Obviously, the issue we suffer compared to metals, if we start back to replacing metals, is composites are orthotropic materials. And in our case, if we mold something with very little flow, it will be transversely isotropic, meaning that you have like quasi-isotropic properties in the plane and a different property out of plane. But as soon as we start flowing the material, fibers realign, and then we are back to orthotropic materials. The difficulty is you need to qualify the different configuration you can end up with. And each configuration, due to the orthotropic or transversely isotropic nature, is more complex than a metal. So that leads you to an allowables database, which is quite extensive. Testing for different load cases, usually ASTM kind of coupon testing, that eventually could also lead to element testing, and then finally part testing. We go up that typical pyramid of certification that most all suppliers have to go through, but it's a bit more comprehensive for composites in general, and probably even more so for us with a discontinuous fiber, which is less common and less known. Obviously, once you have all your mechanical data, so different load cases, different operating point temperatures. We are blessed that PEAK does not take up moisture, so the wet part of the hot wet testing is not really relevant for us. So that's very appreciated. But once you go through all of that, which is fairly typical in the composites world, then you have obviously to feed that into models which you will strive to make predictive. And so, as Travis initially alluded to, that means process modeling, where you will try to predict how the material will flow, to predict a fiber orientation, and then FEA models, where you use this fiber orientation to then predict mechanical properties of the part, so strength and stiffnesses of your end product. And this is something that Greene Tweed has done extensively over many, many years. And again, seems to be validated by the added part requests and parts flying that we have. We have over 500,000 parts flying nowadays. So starting to get a bit of pedigree with that, and the capability of Greene Tweed being recognized there. I will stress something that Travis also mentioned in passing. One of the things slowing down adoption is the fact that it is a novel kind of materials. It seems difficult to get some engineers to transition from metals to composites. Well, transitioning to discontinuous fiber composites is an additional step. And Greene Tweed is there to work on parts with the customer, to lend our expertise to the customer and to develop parts together, rather than either working in a build-to-print setting where the part may not be ideally laid out for our technology, or conversely, a build-to-spec where some let's say validation would be lacking for the end customer. So we sit in a kind of a middle spot where we will work to manufacturers' drawings and specification, but we will strive to help them define what those are so that it is a good match for our process.
That's fascinating, Sebastien. It's interesting how you have to build up this massive data for the fairly special materials that you're using. Is there a point where you have to, I don't want to say this wrong, but where you have to kind of assess, is it worth all the bother? Is it worth trying? You mentioned that you've got to tempt engineers into doing it, convince them sometimes.
And absolutely you do. And that's the point of technology demonstrators. Quite recently, I was personally involved in the hail impact testing of DLF material with the prospect of making several parts. I mentioned vanes, fan platforms are another one. And we hit quite a few typical roadblocks on the way that you would face with composites replacing metals or discontinuous fiber materials being introduced. The typical one was that once we had completed all the coupon level quasi-static testing, that's our allowables. We have a huge database of allowables, B-basis testing that obviously we can go back to when we try to predict capability. But with that known, we had to extend it to hail, like high velocity hail impact resistance. And that is not a standardized test. Each customer will have his own test defined. And the roadblock we had was that the one test that was suggested we use was heavily tailored towards a specific geometry, a specific request of an existing solution. And that was quite a bad fit for our material. And we performed quite badly until we spent a lot of time researching, developing our material, and eventually ended up outperforming continuous fiber laminates of this, like the same carbon fiber peak material. So that was a great thing. But once we were free to play with prototypes, adapting the structure to, well, take into account the shape complexity capability of DLF and adding those ribs, gussets, and all that complexity you can usually never get in composites, resulted in us passing the, let's say, requirements test without needing those highly engineered materials that we had developed for the project, just using our standard DLF.
That's fascinating. And the other thing that I'm interested in as well is you mentioned the use of simulation, FEA, and the data bank that you've amassed. I talk so much about virtual testing versus physical testing. How much does that shape the conversations that you have with customers, with OEMs?
Yeah, so I think what we offer to aerospace customers is the ability to work with them in a collaborative approach. So we have that analytical capability, we have that data set, the B-basis allowables that we bring to the table. So the idea being is there shouldn't be much upfront legwork that they need to do in order to start off sizing appropriately and what have you. And we typically will run our own analysis. We have our own capability, our own methods, but we'll also support them to run their own internal analysis, either at assembly level or part level, because the ideal situation is that we size appropriately before we go into testing.
Great. Thanks, Travis. And I'd like to ask, with this sort of move towards lightweighting aircraft, do we get to a world one day where the default choice for most components within an aircraft are composites, do you think? Or is that never going to happen? And if we are going to get there, when does it happen? Is it going to take a lot more work?
We've seen growing adoptions, not just with our product, but with thermoplastics in general. The aerospace industry is coming to terms with the advantages from a processing perspective, just inherent matrix performance perspective. So some of the customers we've been working with longer, for the past 10 years or so, we are becoming the default, right? So, their engineers, their teams are aware of the capability. They're looking to us for those first part designs versus starting off with some sort of bent sheet or machined aluminum component and then progressing towards an optimization stage. So we are seeing that happening. I think it's going to take some more time. It takes a little bit more just missionary work, so to speak. And we're doing that individually and broadly within the industry. But we are seeing that change start to happen.
Sebastien, do you want to come in? You got any thoughts on that?
One could argue that composites in general are the de facto solution already for certain structures. The latest fuselages and wings have all been composites in the latest airframes, admittedly thermosets in that instance. But I would say that composites have already demonstrated their capability and are the default choice in certain areas. Now, composites need to prove themselves in other areas, obviously where they can play with. You will never have polymeric composites around a turbine, right? It's just a mismatch with temperatures. But they are proving themselves in increasingly complicated cases, and that's where Greene Tweed, not only with the shape complexity capability, but also with the fact that we use a thermoset pre-preg, can have a role, and where we see the increased adoption that Travis mentioned.
To add on to that too, something we've encountered is just almost like an emotional resistance too. So there's a legacy of perhaps composites didn't work out 10 years ago, 15 years ago, and they're the old guard, so to speak, has an inherent bias against using them. And there's one example of the customer, I think there was a manager that had been there for a decade or two, and we continually tried to get our product introduced, and other thermoplastic companies, I think, struggled as well. And when they left the company, all of a sudden the floodgates were opened up too. So there's this bias sometimes that we're working against. And I think one of the things that helps us out is composites today are very different than composites 10, 15 years ago, just from everything we've been discussing so far. The predictive capability, the processing capability, the repeatability. So we're starting to see that industry-wide adoption change a bit.
Yeah, I guess it's just that if it ain't broke, why fix it kind of attitude, isn't it, sometimes? I just have one more question that occurred to me earlier when you were speaking about the manufacturing processes. I hear a lot about additive manufacturing, but here we're talking about molding and pressing. And do you use additive manufacturing techniques and processes at all, or is that's just not in your wheelhouse?
So we have a 3D printer that we'll use to check some fit and form. but it just doesn't function the same, right? And there are processes out there that are better than ours that have a little bit more strength, but there's limitations too. You don't have economies of scale for that. And it's also very difficult to get out of playing Z strength with fibers for 3D printing. So what we're doing is we're chasing after more of a higher volume application versus 1, 2, 5, 10 parts off. And I think we can offer a little bit more strength and repeatability in that sense.
I love 3D printing and I use it on a regular basis. The problem is that printing of high temperature thermoplastic on the one side and then printing of high temperature thermoplastics with long fibers or even worse, continuous fibers is not yet an easy thing. It's expensive. So yes, there is less capex than when you have to have molds to produce any part, and it's great for prototyping, but it is not something that the industry has yet fully solved, and it doesn't scale well. And so in that instance, I think that, as Travis said, for high volume parts, we offer a good solution. We have played with reinforcing locally our parts with local reinforcements that could be 3D printed. And so you strongly reduce the volume needed, the volume of 3D reinforcement needed to only use it where it makes really sense. But this is all very much in the future, in R&D stage. The 3D printing of structural composites, and even more so with high temperature thermoplastics, is still complicated. And we're lucky that it is.
Okay, guys, thank you. I found that chat fascinating. The combination of the deeper understanding and insight, the material science going on, and the information and data that testing gives you and enables you to use these interesting materials to replace metallic components in the way you do, I think is great. I mean, if you guys have any final thoughts or just say goodbye to everyone, and we'll move on with the rest of our hot day.
Yeah, nothing from me.
All good for me.
Okay, guys. All right. So thank you again for your time and thanks for listening.
Okay, appreciate it.
I hope you enjoyed that interview and learned something about how companies like Greene Tweed are replacing metallic components with composites to save weight on aircraft. If you did enjoy it, please subscribe to the podcast for more like it in the future. I hope you have a great day wherever you are.